Hola, the speaker today is Pietro De Checchi. Is going to speak about stochastic unraveling of open quantum system dynamics governed by correlated noise. He's visiting us during 1 month. He's coming from the University of Padova and from the Department of Mathematics. But actually the background is a chemist, the degree in chemistry. The PhD will be in mathematics, and he's visiting us physicist. So let's see how it goes. And thank you for coming. And he's sitting, so he just arrived, so he will be here all month. And he's sitting in the O7, and we'll try to have many meetings with him, okay?
Right, so thank you very much for hosting me for this month and for giving me this time for this presentation. As Roberta said, as I start any conference, I'm a mathematical chemist as a background. In a PhD in mathematics, doing physics, theoretical physics, who knows? So be kind, stop me at any time for any question you might have. Just a bit of background to understand how I moved through all these disciplines. I got my master's degree in chemistry on external topology and quantum dynamics in 2020. Then I moved in Liège to work on atochemistry and theoretical modeling of photochemistry interactions, and now quantum computing and open quantum system in mathematics. So my interest is in quantum system, and in particular the transport energy, with a focus on energy for me, but not what you will see in this work. So how to describe realistic dynamics, and in particular understand how to model features for new artificial applications, which might be quantum computing for and in quantum computing. So using open quantum system to improve quantum computing, or quantum computing to simulate open quantum systems. So a commutative diagram that we always see is this first part, where we have a system and an environment composed together, which undergoes some unitary evolution. And to recover the smaller part that we are interested in, the system part, we trace out the degrees of freedom of the bath. So we are reducing the dimension of our system. Another approach, which is interesting for me for computational and theoretical advantages, is stochastic unraveling. So we take an ensemble of pure states that undergoes some kind of evolution. In this case, I use a set of unitaries, and we will see why. And then by averaging, we obtain the dynamics of the whole system. So this is another way we can unravel known quantum master equation, or use this as a starting point to write new ones. So we start from this point. So as I said, we can unravel the mean dynamics of our system as an average of an ensemble of pure trajectories. From now on, as a mathematician, I will use this symbol for the average. And how do we account for the environment? With some classical noise. So just to stress this point, we don't derive our noise model from some microscopic approach, but we decide what the noise model is. And then we see what are the effects of this maybe unrealistic noise, in meaning a natural phenomena sense, but might be some noises that we can actually use. And we start from this equation, which is a linear stochastic Schrödinger equation that I write on the blackboard as we will use it, so I can keep it there. And it is in its linear form, and then we will see why. So, as I said, the point is to use new processes and obtain new quantum master equation. One advantage of this approach is that we can have a unitary evolution and exploit circuit repetition to implement open quantum dynamics in quantum computers. This might be to the end, or for these days, something to talk about. We can have more information than just the quantum master equation for the system. As a downside, if we want all these things to be true, we might have some limitation on the charts of the operators A and B on this linear form. So, I mean, this was just an animation that I made this morning to see how is an unraveling and how it converges, increasing the number of trajectories. Nothing more, just a not so fancy video. All right, so we start from a linear diffusional stochastic Schrödinger equation, the one that we start from any time. And the point is, we want to have a real evolution of the system, so we must impose a normalization. In this form, right now, due to the noise, we might have something which is unphysical because it loses or gains norm during time. So we normalize using the martingale property, meaning that the average of the norm at each time must be the initial one, which is 1. So we can have a trace-preserving map. And this leads to a particular condition. If we take the differential of the product using Ito rule, we get to this equation that by average must be equal to 0. And depending on the noise that we are going to use, these terms will change and the normalization might change, or some constraints that we have. During this presentation, from now on, I remove the trajectory on the apex just for the sake of clarity. And I use bracket notation and mathematical notation normally with dagger interchangeably. Okay, so start with an example. What we can do with white noise. Spoiler, we can obtain limited force, but that's something that is quite known. So we set our noise in the stochastic Schrödinger equation, the non-normalized one, to be an increment of white noise. So the differential of a Wiener process, which has these properties. So it averages to 0, its square averages to time, and each increment is a normal of variance dt. Then we can write our normalization condition, which by averaging all these terms, can you see? Yeah, okay. All these terms averages to 0, and this leads to this condition of normalization. The point is that here we want the Hamiltonian to be contained in the A operator. So if the noise is 0, we recover deterministic Schrödinger equation. And then we have the normalization term to account for the variance of the noise. So eventually we can write just by replacing our stochastic Schrödinger equation normalized and linear, which we can use to numerically implement this kind of system. And with the similar procedure, just taking C dagger and the differential, and then averaging, we obtain a limited form. In this case, we are using just one operator and one noise, so we don't have the sum over different channels. So this one is just one bath, one channel of dissipation for the system. Okay, so that was what a stochastic unraveling of limited form is with white noise. Our interest is to use different environments, so we introduce the Orsten-Uhlenbeck noise, and that's particularly noise and not the process. Now we will see why. So we have this system. Again, we have our stochastic Schrödinger equation, and we decide that the noise is given by this term, which is the differential of an Orsten-Uhlenbeck process. So theta is the inverse of the correlation time of this process. So we have this first drift term, and then we have some noise, white noise, with its amplitude sigma. We define the noise as as a generalized function. So we use the differential of x, something that will appear here. So if we take this equation and we divide everything by the t, we will have our deterministic part plus B, C. And this noise, similar to what you do for Langevin equation, basically, but with a different noise, a colored noise, and not the white noise. Why are we interested in this? Usually one use Austin-Uhlenbeck processes because they have a clear phenomenology, so damped vibration in molecular system, for example. In this case, we use something different, and that's because we have experimental engineering proof that we can engineer particular environments to our needs. And this year we had a first paper. I mean, we had this group from Eindhoven published a paper showing how they can use this noise in neutral atom quantum computers. To what effect? That's what we're going to see in the numerical results. Let's first start with the theoretical part. So from the system, we can write a non-normalized stochastic Schrödinger equation. And the normalization condition now is different. We have this term, which appears, which leads to a more stringent condition. So the B operator, if you want to stay in a linear form of the stochastic Schrödinger equation, must be anti-Hermitian. And these constraints set us in the framework of stochastic Hamiltonians. And if you're interested, there's this paper which is going to be finished actually in 2 days. I'm under revision. I have a meeting this afternoon for this. But yeah, we can talk about what's the difference between stochastic Hamiltonian and stochastic Schrödinger equation whenever you want. So we normalize. The correction is the same as one that we had before, since we had this constraint, and we obtain an open form of a quantum master equation, meaning that the dynamics of ρ doesn't depend only on ρ, but depends also on each trajectory, on the average of trajectories. So the correlation between the noise that we use to model our environment and the system itself. So I'm going to call it partial correlation recovery, because it recovers some correlation with the bath. Yes. No, exactly. For the white noise, exactly. So for the white noise, let's go for here. The correction term is B dagger B, and we have no constraints on B to obtain this term. So since B dagger B is always Hermitian, B can take whichever form that we want to. So yes, exactly. So it comes here. So for a white noise, we don't have this term. So we're simply this equation. We can move this component here. We know that we have the Hamiltonian, so we have the Hamiltonian plus a correction, and then we get the correction just by dividing by 2 and summing the correction that we want. This term must be Hermitian. Exactly, I want to set 0 this term. Otherwise, what we can do is to use nonlinear forms and find a way to describe A in terms of B depending on X. But this is a different framework and describe different systems. So in this case, we have weak measurements. If we want to go to the nonlinear formulation, it is debatable if we have something which is a weak measurement or actual projective measurement at each time. It's something that I didn't work with exactly because we want to stay in these stochastic Hamiltonian settings. Okay, we're here. So from the linear normalized stochastic Schrödinger equation, we have our Hamiltonian dynamics, the correction term. Then we have this term that accounts, as before with the white noise, to a Lindblad dissipator, plus this recovery of correlation in some way. Now, we can compute trajectories using this form, and in this way obtain the exact solution of this master equation, which analytically can be quite complex due to the correlation recovery term. So what is the effect of this noise? And that's a setting that we are going to use to show some results. So we set the operator R, which is B equal to IR, to be the Pauli sigma x. In this way, for a null Hamiltonian, we can see the effect of the Soul dissipator without having to care about the Hamiltonian dynamics. And then we can see that we have different properties depending on our Hamiltonian. R can be commuting or non-commuting or Pauli noise. And the effect is that we get different decoherence time in our system compared to white noise or Orsten-Uhlenbeck process-driven system, leading in some cases to different stationary states. And this one is another paper that we are going to submit soon, which is on arXiv for the moment and has all the results and much more on the technical part. And again, we had similar results from the same group that published the paper, the preprint about quantum computing, and gets in a different way some similar results. Yes. Then we are going to go to a white noise. Yeah, it becomes a delta again. We are going to an infinite temperature state, so equidistributed state eventually. In this case, yes, since we are, for example, with R equals sigma x, we have an equal probability to jump from one state to another and vice versa. So eventually, we are going to have an equidistributed state, and that's the same for each basis that one can choose. And that's a characteristic and a drawback of the stochastic Hamiltonian approach, which is known to describe only infinite temperature systems. Since we go to different stationary states, I try to avoid the definition of temperature in these systems. And there's also a reason for that, that we can see on the results. First, for a couple system, a degenerate couple system, I want to show you kind of the unraveling, which will explain, which asks me to explain effects or prevent questions about the effects that we will see. So in the first plot, we have white noise. In red, we have just one trajectory. In blue, the average. And as expected, we arrive to an infinite temperature state, like equidistributed state. This one is the effect of Orsten-Uhlenbeck process, so the integral version of our noise. And since it is the integral version, we will see that we have different continuities property of the function. And again, we arrive to an infinite temperature state. With our colored noise, Orsten-Uhlenbeck noise, we have an oscillating stationary state, which is different. And the thing that I will point out just in brevity is that all the trajectories are still noisy. That's something that we thought about for not for a while, but we had a question. Okay, we reach some different state. Does the noise cancels out at some point? But each trajectory is different from the previous one, so that's not the case. In general, for different Hamiltonians, we take a generic Hamiltonian and that we set epsilon and gamma to 0 or to 1, let's say. Doesn't matter the exact numerical value. We see the effect of the Soul dissipator with an Hamiltonian set to 0. So we have two systems, we do not interact and have the same energy. And with white noise and Ornstein-Uhlenbeck process, we know that we arrive at the equidistribution, which doesn't happen for our noise. And again, I will not talk about temperature, but distribution of the state of the stationary state, because this one doesn't mean that we have a population, different population for different levels at different energy, which we can relate to some temperature. But the system has the same energy, so it doesn't really change this particular physics of the system. This is what we've seen before in the previous slide. So we have a commuting Hamiltonian, commuting with the noise. So we have a degenerate system which is coupled, and we will see this stationary state which continuously oscillate around the 1/2 value. And that's true for the population, which I plot here, and it's the same for coherences. And then plot C and D show us what changes when we add some asymmetry in the system. So we have the system which is now non-degenerate. We have different energy using epsilon. And this is an uncoupled system. And this one is the coupled one. And we see that we have a different dynamics, but which will arrive at some point at the equidistribution state. And in particular, in D, it's difficult to see from this plot, I know, but that's what it is. We have a slower decoherence compared to all the other different noise. So that was a first interesting result from this noise. Yes, can depend on the correlation time or the intensity of the noise. I mean, you can use them, yeah.
I am lost 2 or 3 slides ago.
Okay, sure.
You have white noise, are the red, no.
Okay, let's say here.
White noise is black line.
Yes.
The green line is the Ornstein-Uhlenbeck.
The green line is the Ornstein-Uhlenbeck noise, and the red one is the Ornstein-Uhlenbeck process. So, well, I can use this blackboard, so I can just write these. Yeah, the Ornstein-Uhlenbeck process is decaying.
It's decaying, oscillating. No, that was
It's not the Ornstein-Uhlenbeck, it's adding the Ornstein-Uhlenbeck.
Yeah.
We thought what?
Without the column.
Oh.
I understand, just adding the understand.
Yeah, basically, we are in a stochastic Hamiltonian framework. So instead of this, we can write this plus R. Let's use Z for the moment. So this is our Schrödinger equation with a stochastic Hamiltonian. This one is an effective Hamiltonian, and we can use we can use white noise. And so we will have that CT is equal to minus EHT integral dvt S from 0 T. C0 for the white noise. If we set Z to be equal, I'll also write this. X, which is integral of the X. Oh, yes, that's different. Integral of X. T. So we have X, which is the integral version of our noise. So we have an integral from 0 to T of X. And for our noise, so ZT is equal to, which is dx over the T, we have a similar situation to the white noise. So we have e to the minus c, the Hamiltonian component, R. Okay. So this one is the black line, red line, and green line. I don't know if this makes it more clear. If you want more explanation, I can just go on and try to explain better. But yeah, the point is that we have a different fluctuation. One is a process, one is a noise. And they have different properties. Exactly for any function, we can have the function and the integral of the function, which is completely different, which can be completely different at least. So for the white noise, we have the known solution, what one expects. With the Orsen-Uhlenbeck process, we can describe some non-Markovianity of the system already, and we can see it, for example, at the short time in these two examples where we don't have any oscillation of the Hamiltonian, and we can see that we have a different derivative at time 0, which is 0, as one would expect from a non-Markovian dynamics. And in the green one, we have the system driven by the Orsen-Uhlenbeck noise. Okay, so, I mean, all these situations are interesting by the fact that, okay, we have some noise for quite a long time, about a year. We had no idea what it physically represented. And then we thought about, okay, maybe it's something that can be artificially implemented, and that's something that somebody else did, which was really nice to see, and to see that it works. It decays really slowly. It decays really slowly. It has a different decoherence time, and we try to understand why and how to see which decoherence time did we have. So, no, this one is not a stationary state that's oscillating. It will decay and have a mixed state, one half. Yes, yes, exactly. In this case, in these two cases, with these two Hamiltonians, which are asymmetric in a way, so because they are they describe a non-degenerate system, we decay to the one half populations. Exactly. In the never. I mean, numerically, never. And also with the model that we're going to see. So the problem to understand this kind of system is that we had an open form of a quantum master equation. So we want to find a closure model, and we do so using a Redfield approach in a way. Slightly different. So instead of going this way, we are starting again, from the stochastic approach. So we use the usual bottom-up microscopic approach to derive a Redfield equation. So we have a total Hamiltonian, we have the factorization of the system, we have the Born approximation. And from this, well, once we trace out the environment, which is not known yet, or ever, actually, we see that we have a common quantity with the stochastic approach, which is the definition of the correlation of the bath. And what we use for the correlation of the bath, we're going to use the correlation function of our noise. So we can write this. And so what we get is a time-dependent and frequency-resolved coefficients Redfield master equation. So basically what we do is that we apply the first Markov approximation, which is saying that this equation is time local for the density matrix. So we can remove it from, we can shift it from the integral, but we avoid the second Markov approximation, which is taking the limit of the integral to infinite. But it's set to a fixed time t. So we can write our coefficients. They have this form, and already from this, I will just use this thing. You can see that the first part accounts for the Lindblad dissipator, and the second term is time dependent, and just comparing to what we had in the from the stochastic Schrödinger equation averaging, we can write an approximate cross-correlation term. Approximate because we had to do some approximation in the way for the Redfield approach. So this term, which was open and unknown, now has an approximate form, which is similar in a way to a Lindblad dissipator or Redfield dissipator, depending on the frequencies of the system and on the time of the dissipation, of the evolution, of the propagation of the system. And looking at this coefficient and the weights that we get from the rotated operator, we can understand why we are not decaying to the equidistribution and why, and which are actually the correlation time of our system, the coherence time, sorry. So that's the form of the coefficients for different Hamiltonians. A common term is the pure coherence term, which is basically the diagonal term in the Redfield tensor, which is real and decays to zero. So this accounts for the initial decoherence of the system, and then it is null. So if we don't have any other contribution, the system will stay in this coherent state. And these other coefficients are for the different Hamiltonians. So we have the coupling Hamiltonian, the generic Hamiltonian, and this one is just uncoupled non-degenerate system. But we don't have only the coefficients, we also have to look at the operator. So for example, in the easiest example, we take our Hamiltonian to be this. So degenerate system, but coupled. We have to diagonalize it, and that's quite easy. It's just a sigma z operator. So okay. And that's the same here. Sorry. It is the same for this operator. So the rotated operator will be sigma z. So we have the contribution of the pure decoherence, on the diagonal terms. But the other term for this, I mean, everything is a two-level system for the moment. Just for simplicity to explain the model. They have a weight which is 0 due to the operator. So we don't have any contribution from this part, and the system remains coherent and continue to oscillate. For a different Hamiltonian, for the generic Hamiltonian, we are going to rotate again, and by diagonalization of the Hamiltonian, and we will have some terms here, which are much smaller as a coefficient to the previous one. And so we have a different decoherence time due to these coefficients. Or this one, that is not multiplied by 1 or the difference of energy, by a ratio of the difference of energy and the coupling of the system. Okay, so what if we compare the red field that we just wrote to the stochastic Schrödinger equation? Well, we have good agreement, but we see that we have these different oscillations here. Here is for the sigma x noise, and this one is for the sigma z. It's just pictures that I took from the paper. So we have different oscillation, and we are trying to understand why. And we look at the evolution of the eigenvalues of our density matrix. And we see that in the red field approach, for the different Hamiltonians, usually they stay the same. For the generic Hamiltonian, we have some oscillation. This is something that we can discuss further, maybe later. Just one point which might be of interest. So this oscillation will increase over time, and eventually we will have negative values of our density matrix, which is not something that we want. And we try to understand why. And between the two papers that we published, you see the explanation, and you can derive it for many systems. We can show the SSE eigenvalues just for the first one, the red field, which is oscillating, and the red field without the imaginary component. So not the circular equation, but just removing all the imaginary part from the off-diagonal terms of the tensor, elements of the tensor. And we remove the oscillation. And we will have an explanation for this, but it requires a different mathematical treatment to derive it, so we can talk about it later with the questions. So I don't know how long I am, because that's kind of the end of this first part of my work, and then it could be an overview of correlated research, but it's all different topics. So as you prefer. I have no idea. Okay. Okay.
Just one question.
Sure.
The part that the noise does not mutate is
In the red field, or you want to see?
before.
Okay.
Yeah, this one. You have like the noise kind of create the coherence free space.
We thought about that, and we don't think so. We are not in a decoherence-free subspace. There's different effects. And we explained with the red field, but it shouldn't be a decoherence-free subspace in the sense that it usually is thought about.
Yeah, but if you look like, for instance, look in the average equation, the linear matter equation, you get this term that looks like a commutator.
Yes, it's a commutator.
So in this case, does this term cancel the noise or something like that? I mean,
It doesn't cancel the noise.
A finite system, you would, with decaying, any decay, you go to a stationary state, right? This term cancels the noise.
The point is that it doesn't, it shouldn't do it here. And that's the exact point where I was showing this, that every trajectory has a different behavior. So all trajectories are still noisy. So it doesn't cancel out, meaning that we have one term minus the same term.
Yeah. Yeah. Yeah.
So yeah. Mhm. Sure, as you prefer. Yeah, I will just go quite fast. So one first idea is like, okay, we have this system which maintains, let me see where I have it here, maintains the coherences in some way. So one thing is called densification of the block vectors. So here also helps with the questions that we had before. Here we have a system with white noise, and we see that we go to an ensemble which is equidistributed on the block sphere for the two-level system. And with our noise in orange, these are just, I think, 50 or something trajectories. We're staying compact, more dense towards one value, but all trajectories are actually different and still noisy. So here is a snippet, and we can see just for these trajectories, here we have the average. In blue is the white noise, and in orange is the color noise. That we have this densification, and I'm starting this work in a collaboration with Francesco Campaioli from the University of Melbourne to write a measure of densification and try to see what we can get out of this, and not just a measure. That's one point at the beginning of the presentation, which is a master equation just describe the average state, and from stochastic unraveling we can have much more information if we want. We are going beyond the simple one qubit system and checking for something different. We have kind of the same situation for our system in this setting. And one question that I had for Roberta in our first meeting is that, can we use this noise to synchronize qubits? I still have to check it out. I have some results adding a coupling between the qubits, which shows different oscillation, different frequencies, but I don't know if there are frequencies that comes from the Hamiltonian or not. It's just a computation that I set, and then I start writing my thesis. So that's it. Another thing that I'm doing is a generalization of the Rosen-Uhlenbeck process to see what happens if we add something different. Again, just as a mathematician in this case, out of the blue, okay, I add something, let's see what happens. From the physicist point of view, it has a clear physical definition, because we see the noise of a stochastic harmonic oscillator, and we can have three different expressions. We can have the x, the v, and also the integral of the x, so just x. So we can see the position, the velocity, or the acceleration of this oscillator as our term accounting for the environment, and we see interesting results. Again, they're similar, kind of the same, but not we expected from our previous work, but that might be a lengthy and kind of open discussion. And to conclude, I haven't talked about quantum computing. So what I'm searching for now is how to implement in a better way this kind of algorithm. So quantum classical noise algorithm is basically just an algorithm where you insert the noise classically, and you can exploit the fact that all these unitaries might be different due to the noise of your quantum computer, or something different, whichever you want. But this requires quite a lot of repetition of different circuits. So question was, okay, we cannot clone quantum states by the no-cloning theorem, but can we copy states instead of clone them? We can prepare a target state, maybe a difficult state to prepare, and then we can copy it, forking it to different registers, and then evolve them independently in this kind of way. So we have a control swap from, in this case, for simplicity, is a qubit state. You can represent these in qubits if you want. In the simple example, we set Q0 to represent our wave function, and then we fork to many different accessory qubits. And I started this work with Federico Gallina from the University of Ottawa. And yeah, and that's it. And these kind of things can be used for many, many things. We hope for, at least. So thank you very much for your time and bearing with me for such a long time.
So maybe we can start. Are there any questions from home or wherever you are? Just okay. If there are, you just enter and start to shout. If not, we ask here. Any question from you? Now you can continue if you want. It's just Emilio.
I'm confused on several points on the thematic formulation, but let's go to the first, to the initial one. Initially, when you talk about the Schrödinger equation, I was thinking that it was a wave function depending on space, but now all your examples are in two-dimensional, two-state systems.
Yeah, exactly.
But then my question is about the operator B. So yes. B, or better, what is X? Is a two-dimensional vector?
For this kind of system, yes, can be even just a scalar if you want.
Well, it could be different. I mean,
yeah,
so I'm asking about the correlations between the components of the.
Can be different depending what you want to describe. So, for example, for a D-level system, you might have a B operator which is D-dimensional, D squared, of course. And let's take the simplest example. So we are coupling in a similar way to this sigma x, from the Pauli x. We are coupling all states in this simple form.
That is A or B? What is this? Which matrix is this?
This one could be, I mean, with the I in front is B. In our setting, but it can be really anything. Did I use enough?
No, my question is about the correlations of the noise.
Yeah. And then the X can be something which is a scalar, a real value. And then basically we are taking our system, which is 2, 3, 4, a 5 level system to be embedded in the same bath and experiencing the same
noise, all the components.
Not just the same noise, but the same exact environment. So basically, this would be a spatially completely correlated noise. So it is exponentially correlated in time, but in space, it is perfectly correlated. That's one example.
No, I am asking this because I was thinking that it was a Schrödinger equation in space variables with infinite dimensions, and then is when you do this in classical systems of Brownian particles, and you impose that some density should be conserved. What you get is this B is a derivative operator acting on the what is to the right, and then so in other sense you write the Schrödinger equation as a conservation equation, then naturally the noise enters into the fluxes which are conserved.
Yeah.
But here, well, I am trying to
Yeah,
relate
it's a-
this to some
in a way-
classical equations for
Yeah, no,
Brownian
in a way,
particles.
it's kind of a simpler equation to write. I think what you described could be more related to the hierarchy of pure states case, for example, where exactly the B is the integral of a series of time derivatives.
Okay.
Other questions?
Okay, so I just wanted to ask about this, what you wrote on the board there.
Yeah.
Does this represent the usual time evolution of the wave function in the Schrödinger picture?
This part?
Yeah, with blue letters.
Yeah. Yeah, in a way, it represents the usual formulation that we can have for a Schrödinger equation, just with an effective Hamiltonian. So to have
Hamiltonian plus the noise term there?
Exactly. So the noise term is a fluctuation of some parameters of the Hamiltonian. And to recover rho, we still have to average. And it's a different way how we can write this. So this formulation is interesting because we can see that we have a unitary, and then we can decompose it by Trotter, by Magnus expansion, and whatnot, however one's prefer, and implement it on a quantum computer. And that's true as long as we say, okay, B is anti-emission in any case, also for the white noise. Otherwise, this two doesn't work as well, because we cannot write this as a unitary.
So this assumes that the Hamiltonian there commutes at different times, right?
Yeah, in this case, I just wrote it like this as the Hamiltonian. I set it time independent for simplicity, not to write the integral.
Time independent. Okay.
Yeah, exactly. Just the simpler case to avoid the cluttering.
Another question: how? Because I'm not familiar with this field. How is the sigma x matrix arbitrarily chosen in this Hamiltonian there, omega sigma x?
Sorry, how the sigma x is
Yeah, it's
arbitrary?
arbitrarily chosen. This is the Pauli matrix, right?
Yeah, exactly. I mean, it's a choice.
You can choose sigma y, for example.
Yeah, exactly. You can choose sigma y, sigma z, and anything. We did it. And if you do the same kind of reasoning that we did before for the Redfield coefficients, you see that you actually decay and you don't maintain coherences because you have the first term of the Redfield component. You have the pure decoherence, which is set to 0, but all the others which are not. In the same way, yeah, if I set this to be my Hamiltonian and this to be the noise operator, and then I change it, with the sigma x, I get a sigma z, and I get only pure decoherence. If I start from a sigma z, then by the same rotation, I obtain sigma x. I don't have any pure decoherence, but I have all the terms for a different mix of frequency of the system.
Thank you.
Thank you. So maybe we can have a discussion about, I had some question about the derivation of the Redfield, where
Yes.
the microscopic form remains into the R and these kind of things, but we can leave this for a separate discussion with people that are interested in details of the calculation. And maybe just a general question for to conclude now is you have mentioned this application. Can you just say couple of words about?
Yeah, sure. So these are not applications that we did, it's from a different group.
Yes.
But basically the point is that, okay, we have some environmental effects that we described with this noise. We don't know an environment that does that, but can we engineer it? Yes. And what we can use in a quantum computer, basically lasers, pulses, or anything, control fields or fields that we can use to act with some gates on the system, which are noisy. And can we add or counteract this noisy effect with this kind of formulation? And the reply is yes. So basically, that's another thing that's important to care about the stochastic Hamiltonian, because this fluctuation is a term in the Hamiltonian, and we can set the poles inside the Hamiltonian and describe the whole system and change the parameter of the poles depending on some noise and have some control mechanism. So we can maintain coherences for a longer time. For neutral atoms, for I think also ions and so on, you can have optical tweezers that moves the atom, and you can encode already in the optical tweezers this kind of effect, so to maintain this system coherent for a longer time.
What I don't understand, I think, is because in the first figure, when you had the green, red, and black,
Yeah.
like if I understand now, you just had two level systems that were with the same energy.
Yes. Here, the first two.
How can you engineer something that will distinguish these two levels? Because then you end up with a different population in each, right? So I don't know what is the physical thing, I guess.
So I have, I'm not sure about the answer for this, but I have some guess and starting point. So for the null Hamiltonian, we just really don't care that much. I mean, an Hamiltonian set to zero basically doesn't describe a quantum system. So we have two different things. We do not interact, does not have an energy, distinct energy. So we don't really care about that. In this case, we have the oscillation between the two systems. So we don't care which one is which. And this could be, for example, two excited states of two sides. So like an excitonic system. So we have our two levels which are coupled, and our space will be only this one. And we act on this coupling with noise. And we don't care which site is which in our basis system. And in these two, again, kind of the same, because we care about the oscillating one, and we are still going to have an equidistributed distribution as a stationary state. So eventually we will go there.
Okay, so that first figure is just to see.
Yeah, just to see the effect of the, yeah,
Okay.
just to see the effect of the dissipator alone, what it does, without having to care about fluctuation. Because if you see the differences, for example, using different operators, you see that you might have a slight difference in frequency, depending on the noise that you choose. And that's an effect. Okay, it is interesting, but depends on the Hamiltonian of the system. What is the effect of just the dissipator? Okay, I can see it here. And I mean, these are not to scale because they're all different to show in a better way. But if you shrink this one, you'll have this line, which is exactly the one that you get here. Because it's the same noise, the same system, same parameters and everything.
Okay.
Yes, so another question on this slide. I don't understand why the green one is not between the black and the red. I mean, the Oster-Uhlenbeck is like the integral of the white noise with an exponential kernel, and X is the integral of the white noise. So X should be more regular than any of the others. I mean, should be the extreme, the most different from the one which is different from the three. And I expect the Oster-Uhlenbeck to be in between the other two. But I don't understand this result at all.
I expect that too, as well as I expected to have an effect on the short time rather than in the long time, with something that we expect from a non-Markovian system, non-Markovian dynamics, is that we change this first part of the description. In a Lindblad, you always have an exponential decay, even at time 0, before the system starts to interact. And I expected something similar to the Orsten-Uhlenbeck process. And really the explanation that we got is just the one with the red field. So you can see the coefficients and see that you can hinder in some way the pure decoherence of the system to avoid pure decoherence effect. But yeah, it's true. And that's exactly why I said that we got something, that I got something unexpected for the stochastic harmonic oscillator as a noise instead of the Orsten-Uhlenbeck process and noise. Again, as I said, we can have the velocity, the position, and the acceleration as a noise, and we have different regularities. So the acceleration is impulsive, so it's an actual noise that we expect. Then we have something which is continuous but non-differentiable, which is the velocity, and then the position is the integral of all of these. So it is one-time differentiable, it's regular, it's C1 at least. And we get something which is, to me, is kind of weird, because we have a similar effect between the noise and the process. And one of my conjecture, let's say, about this kind of system is that if we deal with colored noises, then that's something that we can use to maintain the coherences of our system because of this kind of counterbalancing effects. And it's something that we do not see here. And this, by the way, it's a generalization of the Orsten-Uhlenbeck. So if I take some parameter to 0, which is the oscillation of the frequency of oscillation of our oscillator, this one should reduce to the Orsten-Uhlenbeck noise and the Orsten-Uhlenbeck process. So this one should decay to 0 again as well, instead of oscillating in a different way, and again with infinite time coherences, which is weird. So exactly, this one is an open line of research.
But this has been studied a lot. The stochastic, the linear oscillator with noise, with many kinds of noise, has been studied.
That one is studied, but in this case is the noise on the system is a noisy oscillator instead of an oscillator with some noise. So there's not that much actually on this exact system.
No more comments? No? Thank Pietro again.
Thank you for having me.